Victor. I'm going to present the experiment 8. We're going to explore the Faraday's law and how the charged magnetic field is related to the voltage induced in a coil. These equations tell us the induced voltage and electronic force depends on how quickly the magnetic flux through the coil charges. In this class, we're going to study the relationship by dropping magnets through the coil, measuring the voltage generated. Your goal is to observe how the voltage change when the varied strength of the magnetic field while keeping other variables constant. As a prediction, we expect the magnetic field increases at 20%. Induced voltage will also increase about 20% since these values are directly related according to the Faraday's law. During the experiment, we will collect data, analyze the percent charge change, and compare your results with your predictions to better understand the physical phenomenon. Thank you so much for listening.
Hello, my name is Jorge Ceniceros, and I'll be going over Lab 8 data and data analysis. So for this lab, we had 3 different samples. We had the base, sample 1, and sample 2. For our base, we had the tube cylinder. The reason we put the tube cylinder as our base was because it has the lowest magnetic field, which was 2 milliteslas. For sample 1 was our rectangular prism with 3 milliteslas, and for sample 2, it was the cylinder with 42 milliteslas. Now our percent difference, we were able to calculate this using our equation base minus sample over sample times 100%. And we got a percent difference of 0% for the base. For sample 1, we got 0.33%. And for sample 2, we got 0.95%. Now for our second table, we had the results of the EMF induced in the coil for each magnet. We had to drop each of these magnets and then see what the average EMF was. And we got a base of 0.02 volts for our base, which is the tube cylinder, and the percent difference of 0%. And now that percent error was also using the equation base minus sample over sample times 100%. And we had sample 1, which was 0.012 volts, which we had a percent difference of 0.66%. And also sample 2, which was 0.003 volts, with a percent difference of 0.33%. And that was our data and data analysis for Lab 8.
Procedure. To begin the procedure, we first set up the apparatus by attaching one of the selected coils to the stand using a clamp. The coil was positioned vertically so that the magnets could fall straight through its center, and the cushion box was placed underneath the coils to safely catch the magnets after each drop to prevent them from breaking. Next, we connected the voltage sensor to both ends of the coil and opened the capstone. On the first page, we created a voltage versus time graph and adjusted the sample rate to 100 Hz so the induced voltage spikes could be read clearly. On the second page in capstone, we selected a digital display to measure magnetic field values using the magnetic field sensor. After the setup was complete, we chose one magnet to serve as the baseline magnet for comparison, then used the magnetic field sensor. We measured the magnetic field value, proceeded to each magnet. Once those values were recorded, we calculated the percent increase or decrease in magnetic field strength for the other magnets compared to the baseline. To make sure the experiment was fair, we developed a method to keeping time of motion as consistent as possible for each trial. This was important because the only factor that was supposed to change from one trial to the next was the magnitude of the magnetic field, not the way the magnet moved. So we also made sure that the same pole of the magnet entered the coil first every time. Each magnet was then passed through the coil 5 consecutive times. For every trial, we measured the amplitude of the positive voltage spike on the graph. After collecting the 5 values of the given magnet, we averaged them to determine the EMF for the magnet. Finally, we saved all well-zoomed screenshots of the graph with the values and annotated it for later data usage. Materials. For this experiment, the materials used were a coil, a strand with a clamp, a cushion box, several magnets with different magnetic field strengths, a voltage sensor, a magnetic field sensor, and the capstone data collection software. Each material played an important part in helping us test Faraday's law of induction. First, the coil was one of the main components for the experiments because it was where the induction voltage of EMF was produced, and when a magnet passed through it, the coil was attached securely to the stand and clamp, which helped keep it stable and centered so that each trial could be performed as constantly as possible. The magnets were used as the changing magnetic field source, with the purpose of the lab was to study how the magnitude of the magnet fields affected the induction voltage and that we used different magnets with, compared them to their field strengths. To measure these strengths, we used magnetic field sensors, which allowed us to record and compare the magnetic field value for each magnet before running the trials. The voltage sensor was connected to both ends of the coil so that we were able to measure the voltage induced as each magnet passed through the center of the coil. This data was displayed and reported using Capstone, which was set to show the voltage versus time graph. The sample rate was adjusted to 100 Hz so the graph could capture the voltage spikes clearly as the magnet moved through the coil. Finally, the cushion box was placed underneath the setup to catch the magnets as they fell, to avoid them from breaking or preventing any damage to the magnets, and then making a new magnetic force. Altogether, these materials allowed us to collect accurate voltage and magnetic field data and analyze the relationship predicted by Faraday's law.
And procedure Pablo. For video editing, recoding and conclusion Manuel. For intro and conclusion Victor. Thank you for watching this week's lab report.
Hi, in conclusion, the experiment allowed us to test the Faraday's law and by observing how the charging magnetic field induced a voltage coil. Based on your results, we found the increase the magnetic field led to an increase in the induced voltage, which supports the idea of these two variables relatable. The percentage charge in magnetic field NF were similar, showing that your prediction was mostly accurate with the small margin of error. Some small difference in your data may have being caused by experiment limitations, such as slight variations in the speed of magnet and the passage through the coil. The measurement is inaccurate, however, overall, the trend remained consistent. In the second part of this experiment, we are also able to increase the induced voltage by charging another variable, such as the speed of the magnet. This further confirmed that the rate of charge magnetic flux is what determines the induced EMF. Through this lab, we gained better understanding of how electromagnetic induction works and how physical factors like magnetic field strength and motion affect the voltage induced in a coil. Thank you for watching it, and goodbye.